All right, here we go. Welcome to physics lesson 4.6. We're going to learn today about free body diagrams and what's called normal force. So the question is, what is a free body diagram? So a free body diagram, it's kind of like a snapshot. It's a drawing of your object at one specific instant in time, and on that drawing we're going to label all of the forces on the object. All right. Now, we've been doing a lot of these. I shouldn't say. We've been doing some sort of rudimentary versions of these. All right. So, for example, we've already done problems where you've got whatever a box, and then Roy is pushing it. So you've got here's the force of Roy, and then maybe you've got Sally or friction or something pushing against in the other direction. Maybe this guy is 30 newtons, and maybe this is whatever, negative 20 newtons. All right, and we can identify our net force, which would just be 30 newtons minus 20 newtons or plus negative 20 newtons. So you get a net force of 10 newtons. All right, so that's sort of the beginning of a free body diagram. But the problem is that we haven't labeled all of the forces. All right, there are a couple forces that I've neglected to draw in here, specifically gravity, and then one other force, which we're going to learn about here in a minute, which is called normal force. All right, so we'll be adding in those forces. And up until now, those forces haven't mattered because all of the motion has been horizontal. Here we're going to be looking at what happens if the force is vertical, okay? If there are vertical forces, I guess I should say. All right? And then the one other thing I'll say is often when you make your free body diagram, off to the side you include a little bit of extra information, such as what the net force is. If you know the acceleration of the object, you kind of write that off to the side, whatever that is. And then if you know the velocity, you'll often write that down, or even just make a little arrow to indicate the velocity. So ultimately, the free body diagram is just a drawing with all of the forces labeled. But I tend to use it as a way to keep my information organized, and I often put other information near my drawing as well. All right. So I guess that's it. So here we go. So let me talk a little bit about the general process that you're going to follow to make a free body diagram. All right. So every time I do a free body diagram, I always follow the same 3 steps. All right. Step 1 is to draw the object, just like a little box like I did over here, and then to identify the mass and the weight of the object. I will always, in every problem, you'll be given either the mass or the weight. And so the idea is that we can use this equation to find whichever one we're missing, right? So if we know the mass, then you just multiply by negative 10 to get the weight. And if you know the weight, then you divide by negative 10 to get the mass. Okay? So that's always going to be my first step. I'm going to draw the object and then identify the mass and the weight. All right? Second step, label and identify any forces that are given. Very often the problem will tell you, Roy pushes with 30 newtons and friction exerts 20 newtons. So that's going to be your second step, is to identify the forces that are explicitly given to you in the problem. All right? Now, the third step is the tricky one. The third step, you've actually got to stop and sort of think. And I don't mean that in a mean way. I just mean that, you got to think about what's going on here. All right? So what it boils down to is there are basically just 2 different types of problems. All right? The type of problem you're going to encounter the most is problems where you don't know all of the forces, but you do know the acceleration. All right? So when that happens, what you're going to do is you're going to say, oh, cool, I know the acceleration. So I can use Newton's second law to find the net force. So you're going to use this guy, net force equals mass times acceleration, to find your net force. Then, usually what will happen is there will be one force that's missing. So what you can do is, now that you know the net force, you can use the definition of net force to find a missing force. All right, so maybe there are 3 forces here, and we know 2 of the 3. All right, so you'd say, oh, well, cool. I know my net force. I know my first force. I know my second force. And I can find that missing force. All right, so here X would be, some missing force. Okay, so that's the type of problem you're going to encounter the most. All right. So let me stop there on this slide. I'll come back to this in a minute. Let me talk about this other option when we actually get to one. All right. So let's do a few examples of this first scenario. Okay. All right, so let's just jump in by doing an example. All right, so it says here Roy holds a 14-kilogram box in his hands, and I didn't write it, and I wish I would have. Let's assume that it's at rest. Okay. Okay, so step one, draw the object and identify the mass and the force of gravity. So draw yourself a little box, label the mass. All right. Let's see, we got to put in our force of gravity. So to find the force of gravity, remember you just multiply the mass by -10. So I'm going to get -140 newtons. So that's my step one. All right. Step two would be to label any forces that are given. Well, it doesn't really give me any, right? Like it doesn't say Roy exerts X amount of force to blah, 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 blah. There aren't any sort of given forces here. So step two, we're kind of done. Okay? So I'm going to move on now to step three, which is stop and think about what you know. All right? And the idea is for step three, I go, oh, well, it's at rest. That means my velocity is 0, and more importantly, it's constant. Oh, right on. That means that my acceleration has got to be 0. All right? So now I can do this. I can use Newton's second law to find the net force, right? Net force is mass times acceleration. So my mass is 14, my acceleration is 0. So I can write it out. So you get a net force of 0 newtons. We also knew that because of Newton's first law, right? All right. So now that we've done that, now I can do this. I can use the definition of net force to find any missing forces. Well, what force are we missing? Well, we're missing Roy's force, right? So let's do this. Let's see. So I know that in this problem that my net force is, well, it's just the force of gravity and the force of Roy, right? Those are the only two forces affecting the motion of this box. Or lack of motion, I guess, in this case, right? So let's see. Our net force is 0. Our force of gravity is -140. And our force of Roy is our missing force. That's our x. And solve it, right? You just add 140 to both sides, add 140, and you get 140 newtons is x. Oh, cool. That means that my force of Roy is 140 newtons. All right? So there we go. Okay, so let's do another one. All right. Now, the second one here, it says a 14-kilogram box sits at rest on a table. So it's really the exact same thing, except that instead of Roy holding it, now it's sitting on a table. Okay? So the process that you use to solve this is exactly the same, right? You go, okay, well, I've got this box, it's sitting on a table, mass is 14 kilograms, gravity is pulling it down with a force of -140 newtons, right? 14 times 10, -10. Off to the side, you go, oh, the velocity is 0, and it's constant. That means my acceleration is 0. That means my net force has got to be 0. And then you look at your drawing over here and you go, well, wait a minute. I got gravity pulling it down. There's got to be something holding it up. Oh, that's the force from the table, right? Then go through that algebra that we went through before, very simple algebra, and figure out what the force from the table has to be to make your net force 0. And of course, it's got to be 140 newtons, right? All right, now, we are not going to call that force there. We're not going to call it the force of the table. All right? So here we go. The support force provided by the table or any inanimate surface, you know, maybe the box is sitting on a floor, maybe it's sitting on a shelf, whatever. It doesn't matter. It's sitting on some inanimate surface, and we're going to call that normal force. Okay? So this, what I've got here labeled as Ft, as in force of table. From now on, we're going to call Fn as in normal force. Okay? So that is that. All right. Okay, so this time, we've got Ed lifting a dog. All right, so here we go. So draw yourself a little dog. Oh my gosh. This is the worst dog ever drawn by a human being. Oh, all right. I salvaged it there at the end. All right, we got an 8-kilogram dog. So start by putting in your force of gravity. It's going to be -80 newtons. All right? So that's my step one, mass and force of gravity. Step two, any given forces. Force of Ed, 100 newtons. All right, and then since he's lifting it, it's not on a table or anything, so I don't need to worry about normal force here. That's maybe worth noting. no normal force because dog isn't on a surface of any sort. Okay, so that's the only time you got to worry about normal force, is if your object is sitting on a surface. All right, so I think that's it, right? I think those are all of our forces. Okay, so these are actually the easy ones. This is one of these examples, B over here, where you know all of the forces, right? So now what we're going to do is, this time, we're going to use the definition of net force to find the net force. So I can find my net force by just adding up all of my forces. You know, however many of them there are. And then once I know my net force, then I can find my acceleration by using Newton's second law. So that's exactly what I'm going to do over here. So over here I'm going to go, oh, well, my net force is, well, in this problem, there's only two forces, right? There's gravity and there's ed. So the force of gravity is negative 80 newtons. Force of ed is 100 newtons. Add those up and you get 20 newtons. So there's your net force. And then you can find your acceleration. All right, there, cleaned up my board a little bit. All right, you can find your acceleration by doing net force over mass, right? So let's see the net force on the dog. We just found it. It was 20 newtons, right? Because Ed's force was 20 more newtons than gravity. Mass of the dog is 8 kilograms. Divide it, and you get 2.5 meters a second squared. All right. So there we go. So that's those are the two different types of free body diagrams that you'll run into. Ones where you know the acceleration, and ones where you know all the forces. All right. Let's do a couple more here. All right. So here, we're lifting something, but this time instead of telling you the force used to lift it, this time I've given you the acceleration. Okay. So here we go. Step one: draw the box. 30 kilograms. Put in your force of gravity. 30 times negative 10 is negative 300 newtons. All right, and then we know there's going to be a force from Carl, but we don't know how much force it's going to be, right? So that's step one. Step two, I drew in Carl's force, but I don't know what it is, so that was a little sloppy. I probably shouldn't have even put that force in yet, because sometimes you'll think that a force is in one direction, and then you do the math, and it turns out that it's not. All right, so we're down to step three. Stop and think about what you know. Well, I know the acceleration, right? Acceleration is 2 meters per second squared. So I'm going to use Newton's second law to find the net force. So I get a net force of 60 newtons. And now I'm going to use the definition of net force to find Carl's force, right? So let's see, net force is the force of Carl plus the force of gravity. So let's see, net force is 60 newtons. That's got to equal the force of Carl plus my force of gravity. And then solve it, right? Add 300 to both sides, and your x turns out to be 360 newtons. Okay. So there is my free body diagram. Okay. All right. So here's another one. This is, again, very similar. So this time, instead of having Carl lifting the box, this time the box is sitting on the floor of an elevator. So I'm going to start out the same way. Here's the box. Mass is 30 kilograms. I'm going to start by putting in my force of gravity. It's still going to be negative 300 newtons. This time, the only difference is, instead of Carl lifting it, it's the elevator that's lifting the box, right? Okay, so again, you go, oh, well, I know the acceleration is 2 meters per second squared. So my net force is going to be 30 times 2, or 60 newtons. Okay, so, but what's lifting it this time is the floor of the elevator, right? This thing is sitting in, it's sitting in an elevator, and it's the floor of the elevator that's pushing it up, right? So here's the force from the elevator. But guess what? That's an inanimate surface. So I'm actually not going to call it force of elevator. I'm going to call it normal force, right? Okay. And then the math is, it's the exact same thing we just did, right? 60, I don't know, I'm being sloppy now because I'm hurried. Let's see. So our net force is the normal force plus the force of gravity. So 60 equals normal force plus negative 300. and solve it, and your normal force turns out to be 360 newtons, right? So a couple main things I want to point out about this. First of all, it's possible for normal force to lift something, right? Secondly, if you've ever been in an elevator, which most of you have, you may have noticed that when the elevator first starts moving up, you feel a little bit like squished, right? Like something squishing your feet down into the floor. Well, that's because the elevator is exerting extra force to lift you, right? If the elevator wasn't moving, then the normal force would be just 300 newtons, enough to cancel out gravity. But to lift you, to cause you to accelerate, it's got to exert extra force, enough force to support you, and then an extra force to cause you to accelerate. Okay? All right. So now, what happens if the elevator is moving up and slowing down? Well, this time what's going to happen is our velocity is going to decrease, right? Since we're slowing down, our acceleration here is going to actually be negative 2 meters per second squared, right? Because our velocity is going to go from a big positive number to a smaller positive number. Okay, so let's see how that affects things. So, I'll draw the box. Mass is 30 kilograms. Force of gravity is negative 300 newtons, right? Just like before. So we know the acceleration, so we can find our net force, right? Just use this guy, acceleration. Net force is mass times acceleration. And so you get a net force of negative 60 newtons. So, what's the other force? Well, even though the elevator is moving up, even though the elevator is slowing down, it's still pushing up, right? And like the entire time you're in an elevator, the floor is supporting you, hopefully, right? Otherwise you're falling. So here we go. We're down to here, right? We got to find our missing force. So the net force is going to be force of the elevator, the normal force, plus the force of gravity. So our net force is negative 60 newtons. That's going to equal our normal force, which we'll call x, plus our force of gravity. Add 300 to both sides, and you get 240 newtons equals x, right? So our normal force now is 240 newtons. So this is the deal where when you get to the top floors, the elevator starts to, as the elevator stops, you have that moment where you feel sort of like lifted up off of the floor a little bit, or you feel a little bit lighter. That's why that's happening. What's happening is the elevator is moving up. The normal force is a little bit less to allow gravity to win, to slow your upward motion until you stop. All right. All right, let's do another example here. All right, so this time we got Norm pushing a 160 kilogram pony. So write yourself a pony. I'm going to skip the art on this one since my video is already pretty long here. Put in your force of gravity. So force of gravity is just going to be 160 times negative 10, so you get negative 1600 newtons. All right, so that's my step one. Step two, label any forces. Let's see, it says Norm is pushing it to the left. Why did I do this to the left? Annoying. All right, so here we go. Here's our force of Norm, 960 newtons. 960 newtons, there we go. All right, and then it says friction exerts 320 newtons. So the idea is, since Norm is pushing the pony this way, he's going to move that way. Friction's going to oppose that motion. So the force of friction is going to go this way, 320 newtons. That's going to be positive. All right, and we're trying to make a free body diagram of the pony. Let's not worry about this. Okay, so that is that. All right, so step three. Now we got to think about what we know. So here's the deal. Look, the motion here is horizontal. We've done problems like this before, but up until now we haven't had to worry about gravity. And the reason we haven't had to worry about gravity is because, the pony's not going to move up or down at all. So gravity is pulling the pony down. What's preventing him from moving down is the normal force, right? So up until now, we've done all kinds of problems like these. We just haven't included force of gravity and normal force. Now that we're making formal free body diagrams, you got to make sure you include all the forces. All right. So I think that's that. Don't forget that normal force, even though it's moving horizontally. Still got to put in normal force and gravity. I think that's it. So do we know the acceleration? We're on to step 3. Do we know the acceleration? I don't think we do. Do we know all the forces? I think so. I think this is it. I think we got, oh, I just realized I got 2 FNs. That's not okay. So we got to clarify one of these. This is the force of norm, the person, and this is F norm as in normal force. All right, so anyway, so those are all of our forces. We got normal force, norm, friction, and gravity. So now we can use option B there and finish this guy up. So let's see, so our net force now is going to be the total of all of our forces. So it's going to be normal force plus gravity plus friction plus norm, the person. These guys cancel out. So my net force is my force of friction, 320, plus my force of norm, negative 960. Add them up and you get negative 640 newtons. So that's my net force, and then my acceleration is net force over mass, negative 640 newtons over 160 kilograms, and so you get 4 meters per second squared. Okay? So, the problems aren't that much harder when they're long, when there are more forces, just, extra numbers to keep track of. All right, I think we just got one last example here. All right, and this one's actually very similar to the last one, except this time I've given you the acceleration instead of Norm's force. All right, so here we go. So we've got Gus sliding a 60 kilogram copy machine. So 60 kilograms, put in your gravity. It's going to be negative 600 newtons, right? He's sliding it to the left again. Why did I keep doing that? Across the floor, not frictionless, with a force of 270 newtons. So here's my force of Gus. Notice I'm writing his name out to distinguish it from gravity. All right, there's friction, so we don't know what the force of friction is. So we'll have to find that. We know that it's going to accelerate to the left at 2.5 meters a second squared. So I don't know this. I, again, can put in my normal force because it's not going to matter. Because, it cancels out gravity, rather. Okay, so our net force, then. So look, we're looking at this guy, right? We know the acceleration. So I can find my net force by doing mass times acceleration. 60 kilograms, negative 2.5 meters a second squared. So you get negative, 150 newtons. So now I can find my force of friction, right? So now we got to do this. So now, let's see, let me clear up the board a little bit. All right, so now, drop my pen. So now, net force is, well, let's see, it's the normal force plus the gravity plus Gus plus friction, right? These guys cancel out, so I'm going to not worry about them. My net force is negative 150. That's got to equal the force of Gus, which is negative 270, plus my force of friction, which is X. Add 270 to both sides, and you find out that X is 120 newtons. All right, so there you go. All right, this last one is basically more of the same thing. The big thing to notice on this one, I'm going to skip it because I'm already way over my time limit. But here we're going at a constant velocity. Remember, that's just a fancy way of telling you that your net force is 0. Okay, so if you finish this one, here's what you end up with. You can try this one on your own. 150 kilograms. You're going to have gravity, normal force. It doesn't tell you which way he's sliding it, so let's assume he's sliding it this way. So here's the force of Sam. Since our net force is 0, that means we've got a friction. Also 540, just to cancel out Sam's force. All right, there you go.